Okay, so welcome to this second part of discussing association rule mining. Up to now, we discussed the importance of association rule mining, and to do association rule mining, we need to find the frequent patterns, right? So we looked at one algorithm to find out frequent patterns, called Apriori. That's one of the initial algorithms that people came out with. Let's look at another algorithm as kind of an improvement of not an improvement, like trying to reduce some of the problems that we have by having to scan the data set multiple times, right? Yeah, so the idea is to try to mine frequent patterns without candidate generation, right? So whether we can start from patterns and then build up on those patterns, and also reduce the number of times that we have to do the scans, right? Database scans, right? Yeah, so we try to grow long patterns from short patterns using the local frequent items, right? So we still use the same concept of starting from a bottom-up approach, where we start from the high frequent one item sets and continue to grow. But once again, once you look at the technique, you will the approach algorithm, you will figure out, right? So now we can't do this by just changing the algorithm. We also need to have a data structure that can keep some of the information that we keep reading again and again in the a priori approach, right? In this case, what we try to do is we scan it and store it in a data structure and then reuse it from that data structure, rather than having to scan again and again, right? So that's what we are doing here, right? So it's called FPgrowth, or frequent pattern growth tree, or FP tree approach for frequent pattern mining. Once again, still we are looking into frequent pattern mining, because in this association rule mining business, the biggest problem is finding the frequent patterns. Once we identify the frequent patterns, it's not a big deal to look for associations, right? So in the example, the ones who completed would have realized, once we find the frequent pattern, it's a case of looking at the multiple combinations of possible associations and then calculating the confidence. That's very straightforward, right? Finding the frequent patterns is the biggest problem, right? So let's look at a way of doing it, right? So I do have a nice animation thanks to one of the students, I think undergraduate student, about 3, 4, 5 years ago, where I put a challenge asking, not a challenge, I gave it as an extra credit opportunity for to come up with animations for these algorithms, right? So when I was learning data mining in my research group, we used to, my supervisor used to always ask us to animate. Whenever you read a new algorithm, animate it so that you understand it well, and then you can share it with others, right? So yeah, animation takes a bit of time. Nowadays, it's much more easier than those days, but that will help you to understand, right? And help others also to understand, right? Yeah, so I will get to that animation later, but before that, let me very briefly explain what this FPgrowth tree algorithm is trying to do, right? I told you, we can't do it with only a change in the algorithm to reduce the number of scans, right? We need to store something somewhere, right? So that's why you see this tree-like structure on the right-hand side of the slide, right? On your right-hand side of the slide, yeah. Right? So yeah, so we need to have that, right? So let me explain to you how you build it. But before that, let me go through these 3 steps that are given. Step 1, 2, 3, right? First of all, we scan the database like what we did for the a priori, and find frequent one item sets, right? So I mean, in this case, I'm using this small toy example once again, right? So first we identify the frequent one item set, and in this case, we don't just take it as it is. In the second step, what we do is we sort them in the frequency descending order, and we call it the F list, right? So there's this table. If you can see, there's a table next to the steps, right? On that, we have identified the most frequent one is F, C, A, B, M, P, right? So we go down, and also if there is a tie, we can put whatever we want as the first item, but we need to stick to that order, right? Otherwise, the algorithm is going to get messed up, right? So we need to stick to that order. But after that, Yeah, and actually not only putting all the items in the frequency order, we need to put the transactions that we have also into that order, right? So if you go to the top of the slide, you see that the original transactions has F, A, C, D, G, I, M, P. Now we change that transaction into a transaction that only contains the frequent items, and also those frequent items are put in the proper order, right? Proper frequency descending order, right? F, C, M, P, right? That is a frequency descending order, right? And also that is the order that we have selected because when there are ties, we take one first, we keep to that order. Right, and then what we do is we start building this what do you call this FP tree, starting from an empty node. We keep adding nodes to it based on yeah. So actually, the second scan would build this tree for us. Right, first scan would tell us what are the frequent items, right, and then the second scan would help us to build the tree. Right, so building the tree is not shown here, so I will use the animation to show you how it goes. Right, yeah, let's go to the animation. Right, so once again we indicate the table, the data that we have. Right, so the first step would be to find the frequent one item sets. Right, so this is the step that where we have found out the frequent one item sets. Right, so FAC and PB, right, are the frequent, and then we have indicated the we have not put it in the order, right? So we are doing it in two steps, right? And then we create the F list, right, where we put it in order, right? So that, as I said, we can stick to whatever order if there are ties, but we have to stick to that order, right? Yeah, so now we start the process of building this tree, right? So we start with the null, right? Null kind of say node where you don't have anything there, right? And we start scanning each transaction in the database to generate the FP tree, right? The items in each transactions are processed in the F list order, right? Yeah. So at the beginning I said that we take in individual transaction and then drop the items that are not frequent, and also when we take items from that transaction, we take it in the F list order, right? That is the order that we set up at the beginning, right? So if you take the first transaction, it is shown on the slide. We have to take the first F that we have, right? So when we encounter the first F, what we do is because we don't have any Fs in the tree, we create the first node saying F node, and also we put the frequency as 1, right? And not only that, on the header table also we put a 1 for F. That is to say that we have found one F, right? Right, and then we go to the next item in the same transaction, C. Now we need to check and see whether we have a pattern where it says FC, right? So we don't have a FC, we have a F. Therefore, we put another node to F saying, okay, there is a pattern that is building up, which starts from F and then C, right? And once again, similar to what we did for the F, we put a C in, we put 1 to the frequency of C, right? And remember, always whenever we see an item, we update the count, frequency count, right? We do the same thing for A, FCA, right? And M. Now we see a M here, right? We see the M because we see FCA, but we don't have a way of putting M. Therefore, we add a node and put a M, right? And then P, right? So actually, when you take the first pattern, you will be adding nodes each step, right? There won't be any way of reusing the existing nodes, right? So let's take the next one. Again, we have an F. Now, F we already have in the tree, right? So therefore, we don't need to add a F, right? So what we need to do is go and update the count for F, right? Then we have C. What we do is, ideally, this guy should have highlighted the node that is getting updated, but hopefully you can figure out that the C is getting 2 now. C has become 2. B. sorry, A. Next one is A, right? So now FCA, all are having 2 because we have seen FCA, we are seeing the FCA pattern for the second time, right? And then B. Right? After FCA, there is no B. Actually, B is not there at all in the tree, right? So we need to put another node for B. Right? And also remember, when we put a B, we need to connect that B from the header table, right? So there is a reason for doing that. We'll come to that later, but we need to connect that also, right? And then M, right? After B, there is an M after A, but there is no M after B, right? So therefore, we need to make sure that we put a M after the B. Next one, F. We increase F by 3 now, because this is the transaction that we have seen. We are seeing F. Then after F, B, we don't have. We have already seen a B, but we don't see a B after the F, right? So therefore, we need to add the node, and also note that yeah, I didn't note that earlier, but if you see that M's are all connected from the header to the nodes in the tree, we are connecting. Similar to that now, because this is a new B, we will be connecting B from the header to the node, one of the nodes that we have B, and then the other node that we have B, right? Right, so the next, oh, sorry, that's done, right? F and B only in that transaction. Then we get another one where we start. There are no F's in that pattern, right? Transaction. Therefore, we start with C. So we don't have any way of starting with a C. So we start with the C. Then B, the B is connected, right, to the other B's that we have and to the header table, right? And then we have a P, right? So we'll have to put another pattern there. What are the last one? Last transaction. Once again, we have a F. Therefore, see, now F was 3 earlier, now it is 4, right? And then C, okay, we don't need to add any nodes. We can go on the same pattern. A, we increase, right? A was 2, now A is 3. M, after A, there's a M, right? So earlier it was 1, now it is 2, and then P. Right, so FCAMP pattern is saying that there's a frequency of 2, right? Yeah, so that's how you build a frequent pattern. Any questions regarding how you build a frequent pattern tree? You can ask either chat or you can unmute and ask. Right, hopefully that guy has done a good, I mean, I've been using this for the last 3 to 4 years, so I've always been itching to modify this, but I've been able to do it. But anyway, so that guy has done a good job, and I think all of you understand how to do it. And if I give you a table like this, like what I gave you for the Apriori, you should be able to build this. Right, so a little bit before we go and discuss on how we get the patterns from that or frequent patterns from that, let me just tell you some benefits of using the FP tree, because what we looked at is how to build the FP tree, which is a kind of a condensed version of all the patterns that are there in the data set, right? So that's what we want, right? So right, so yeah, so preserve complete information for frequent patterns. We are not losing any information, right? So remember, when a priori in the sampling approach, we might lose some of the patterns, right? So this is not like that. Although we are doing only 2 scans, we are not losing any information, right? And we never break long patterns of any transaction, right? So if there are long patterns, all those long patterns are preserved as long as they are frequent, right? As long as they qualify, as long as the items that are there in the pattern qualify to be frequent, we include them, right? Yeah, and it's compact, right? We definitely remove the irrelevant information, right? Because for example, in Apriori, although we filter out the one item frequent patterns, still when you are scanning, we have to go through those things, right? Although we are not counting them, we have to go through them, right? So that's an issue that we have with Apriori, the standard way of doing it, right? Items are given in the frequency descending order. The more frequent items occurring, more likely to be shared at the top, right? And also something that we can say is that this data structure will never be larger than the original database, right? This tree structure will never be larger than the original database, right? So somebody might argue and say, now you're not scanning the database, but you have to scan this tree to find the frequent patterns. But I mean, there are empirical research, and I mean, we can try to show. I mean, it depends on the data set, right? But we can give a guarantee that it's never going to be larger than the data set itself, right? Right? Yeah. Sometimes, yeah. So yeah, we can think about sometimes compression ratios of over 100, right? So that means if the original database is 100, we can have this data structure at 1, right? 1 MB or 100 GB, 1 GB, right? Yeah. So those are some of the benefits of FP tree, right? So now let's look at how you from the tree itself, how do you build the patterns, right? So yeah, so what we do is we take each item, right? So if you follow this table that we have on the right hand side, we show you the multiple different frequent patterns that are there, and also the frequency of those patterns, right? So yeah, you start from the start at the frequent item header table, right? And then in the FP tree, and traverse the FP tree by following the link of each frequent item, right? And we keep accumulating all the transform prefix paths of the items to the patterns that we have, right? So that's what we try to do, right? So yeah, so if you take the first example that we have, if you take C, right, CF, right? If you look at C, the patterns, conditional patterns that we can create from F and C, it's 3, right? So how do you find that it is 3? If you look at on the tree, you see that for FC we have 3, right? And then yeah, C by itself is, we don't put it as a pattern, right? Well, that's not there, right? So then we'll take A, right? Now look at A. We have only one A, right? Because we have to start from the header table, right? So we have A, right? If you look at A, we have only one A, right? And the only pattern that we have is FCA, right? So with item A, we can create a pattern FCA with a frequency of 3, right? Then we take B, start from the header, right? B, frequency of 3, and then we follow the links from the header, right? So B, there is one pattern, we find one pattern, FCAB with frequency 1, because the frequency will be always the number that you have at the bottom, right? The number that you have in that node, right? So B says 1, that means FCAB pattern, we have it with frequency 1. And now then we look for the next B that we can find, right? What is the next B that we can find? Once again, it's a pattern FB, right? So we put F there to say that with B we can create another pattern FB with a frequency of 1, right? And then there's another B next to it, which would create a pattern with C, right? So that's why we put C. Is that clear? Can you follow and figure out how you make the patterns for M and P? Right? Is that clear? This part should also be animated so that it's easy for you to figure out what's going on. Let me roll back a little bit, right? So we start from the header table, right? Right. So if you take, I mean, we are looking at, yeah, and you might be wondering why we don't have any patterns for F, because F is F and C are at the top, right? Right. So anything I mean, by itself we don't create patterns, right? So I mean, we know that there are anyway frequent one item patterns, right? So we start with the first second level node, right? The C, right? So that's why we start with the C, right? So we see that there's a frequency of 4 for C, and then we follow the links on the tree for the C, right? So C, there are two Cs, right? C3 and C1, right? C with frequency 3, C with frequency 1. Frequency 1 we don't take because it's at the first level, right? C with the frequency of 3, we know that we can create a pattern with F which with a frequency of 3. Then we take A, right? A has only 1, therefore we can say FCA with a frequency of 3. Right, so by going through this, we can find out all the frequent patterns that are out there in this data set, and then we can do the associations for those patterns, right? So that's an easy way of finding frequent patterns. Yeah, so this is a small comparison of FPgrowth and Apriori. What I want you to see is that, and also, I mean, obviously, FPgrowth will have less time, will take less time. And you see that the Apriori runtime is going like in a exponential scale, right? You can't, in certain points you can't even see, right? So I mean, if I explain to you what the two axes are, right? So we have the runtime on as the y-axis, and on the x-axis we have frequency threshold, right? So that's also something that you should realize. When we have I mean, if you are looking for low frequent item sets, it will take more time because we have to do a bigger search, right? So especially a priori, we have to do a bigger search. The candidate items are going to be huge, right? So in this case, when you go for a frequency of less than 1%, you can't even do it. I mean, I don't know what this is a standard data set, right? It's a very good point to explain to you, I mean, about benchmarking, right? So especially for these types of algorithms, we do have benchmark data sets, right? So if you come up with a better algorithm, then now I explained to you two algorithms, right? If you can come up with a better algorithm and then this, what you should do is you should run it on this standard benchmark data set, right? And show that your curve is better than these two curves that we have here, right? Right. So yeah, anyway, what I'm trying to say is that FPgrowth is better than algorithm a priori, and also there could be, I mean, at a higher levels of what you call threshold, there could be maybe places. I mean, this graph is to coarse. That means not granular enough, fine grain for us to see those deviations. But in general, what you should understand is that a priori, FPgrowth will do a better job, and you know why it is, right? So we already saw that, right? Yeah, so why FPgrowth is a winner, divide and conquer, right? So we decompose the mining task and the frequent pattern generation to the two steps, right? Yeah, and also this, because of this, we represent the patterns in a tree, and then we do the search in the tree, right? Not in the data set, right? Right? So we represent everything in a tree. We represent all the patterns that are there in the database in a tree, and then we do the search in the tree, right? We spend most of the time in the tree, right? Yeah, so no candidate generation, no candidate testing. We get a compressed database, which is the FP tree. No repeated scans for the entire database. Most of the time, what we're doing is counting local frequent items and building the sub FP tree, right? No pattern search and matching, which we have to do in the a priori. Yeah, so very briefly, this is the third approach that I showed you earlier, right? So I said a priori, FPgrowth, and vertical data formats, right? So these are the third approach that we have. Right, so the idea of vertical data formats is that convert the data set into vertical formats, right? So, right, so if you look at this, if you can remember, I talked about this in databases, bitmaps. Do you remember the bitmaps? I told you that was one of my favorite topics, right? And so what we do is we take the transactions, and for each item set, we create a bitmap, right? So if that transaction is if that item is present in a transaction, we put a 1. If it is not present, we put a 0, right? So if you look at the example for A is there only in transaction 10. 10 and 30, right? So therefore, we have 1 on those two places, right? So after you create the bitmaps, it's just a case of ending operations to check and see what are the items that I mean, what is the frequency of a given pattern, right? So if you want to find whether AB is a frequent pattern, you do an AND of A and B and find the count. And also by just doing the individual counts for these bitmaps, you can find whether they are frequent or not, right? Or else what you could do is, we don't do that actually. What we do is we find we do a scan and find the frequent pattern, find the items, one frequent items, and then drop and build the bitmaps only for things that are above the threshold, right? And then we do the ending, combinations of ending, and do the counting to find out what are the frequent patterns, right? Yeah, so this is given here, right? A, B, C, D, E, and then we do the endings. And yeah, so there are multiple algorithms. Multiple people have come up with different ways of doing. The Viper is one of the algorithms. I don't know why they call it Viper, because maybe the bitmaps are like snakes, right? Viper is a type of snake, right? But Viper has, I mean, it's an acronym, right? I can't remember off the head, but that is, if you search, you can find out, right? V is definitely vertical, right? So yeah, so that's what we have. That is what we have there, right? So as I said, that I don't want to go into detail, but you can explore it further, right? And also, as I'm challenging you, if you can think about ways of doing frequent pattern mining in an efficient manner, think about it and see whether you could come up with a new approach to do that. Yeah, so visualization, once again, these visualizations are not the greatest visualizations out there at the moment. But now for when you talk about frequent pattern mining or association rule mining, how should we visualize it, right? What are the important things? One important thing is the support, right? And another important thing is the confidence, right? Hopefully you remember, right? Support means how frequently a pattern is occurring. Confidence means for a given rule, what is the conditional probability? When this happens, what is the probability that the other thing is going to happen, right? Subsequent and the consequent, right? So what is the probability of the consequent happening if when the subsequent happens, right? So that's what we are about. That's what we need to highlight, right? So in this visualization, although it is not the greatest visualization out there, we are showing both all those things. And also we would like to see from a visualization point of view, we would also like to see what is the item that we have on the left hand side and what we have on the right hand side. So on the axis we have the left hand side and the right hand side, and on the with the size of the bar we are showing you the support, right? And then with the color map or heat map type of approach, we are showing you which one is the best, I mean, from a confidence point of view, which has the highest confidence. Right, so let me very quickly ask you a question. What do you think is the, I mean, in your opinion, what would you consider as one of the best associations from this visualization? Can you very quickly post it on the chat? Hopefully you can see this clearly. Let me give you about 1 minute. What would you think is, yeah, the heights are not very clear, but I mean, based on what you can see, you don't want to commit yourself, huh? Any thoughts on, guys? Take a chance. I'm not going to add this to the final. R0 and L0, yeah, you're right. Thank you for us. R9 and L12, R9 and L12. Yeah, because obviously, I mean, support is important, but in most cases, I mean, it depends on your application, right? In most cases, confidence is very important, right? So red confidence or very close to red confidence means they are very good rules, right? I mean, from a confidence point of view, they are rules because that right? It's not just appearing there because it's frequently happening. Frequency is also important, right? Without frequency, high confidence is also not important. But once it's beyond the required frequency, um, the confidence is the key, right? So yeah, so this brings us another important topic, that is just because we have patterns, we don't take it. They are not useful. The patterns should be interesting. Patterns should be able to bring us revenue from a business point of view, right? So the patterns can bring revenue to us only if these patterns have high confidence and high frequency, right? So yeah, right, okay. I'll go from here because thank you. A lot of people are answering now on the chat. Thank you very much. Yeah, right. So let's go into the next slide. Yeah, this is another way of, I mean, very good question from one guy. Yeah, he's asking how do you find the direction of the association? Yeah, actually, that's a bit of a shortcoming on this visualization. I told you, right? This is not the best visualization, right? So, yeah, so because it indicates left hand side and right hand side, we have to take it like L naught implies R naught, right? Okay, so that's right. But maybe from the visualization point of view, also, if that was obvious, that would have been great, right? But yeah, I don't say it is not there. It's there because they have named LHS and right hand side, right? So always the rule goes from left hand to right hand side, right? So it's there, but it's not very indicative, in my opinion, right? So there's another graph here as an example where we have gender. What are the attributes is not important, but what in this type of graph type of approach to show associations is because most of these patterns, if you take these frequent patterns, the items that are part of frequent patterns are common most of the time, right? So visualization like this could help us to identify that, right? So especially in bioinformatics applications, this might be very useful. And once again, in this visualization, we show the support with the size of these whatever spheres that we have, and then the color is showing you some form of confidence, or yeah, right? So once again, I'm not going to dwell too much into this visualization. Another way of another visualization in this once again, I apologize for the crudeness of the visualization. These are taken from the original slides of the textbook, right? I hope they have improved it by now. I took it long time ago and I'm still having those slides here. Right. So in this one, we are once again showing the very similar to the first graph that I showed you, but in addition to saying left-hand side and right-hand side, they are showing the actual items that are there. So that would be a better way of visualizing. That would be a better way of understanding. But otherwise, in the previous case, you need to find what these left-hand side items are, right? Right. Here we are showing the items in this visualization, right? So that's the one. But that's the point that I wanted to make on this one. Yeah, we have another small exercise, but due to the time constraint, I will not ask you to do it now because I want to complete this in about another 10 minutes. The remaining slides, we have about 14 slides to cover. So I would ask you to, when you go home or when you take your lunch break, after your lunch break, if you have some time, try to go through the second quiz that I have given. Once again, these quizzes are practice quizzes, and I would encourage you to do it today itself so that you can solidify what we have discussed today, right? Yeah. All right. So this last part of the session is to talk about other extensions to one of you guys asked if one person buys 2 items and another 1 item, how do you consider that, right? So those are the different variations or different extensions that you can make to the standard association pattern mining algorithms that we have, right? So yeah, mining yeah, so let me list down a few. We're not going to look into algorithms. That would take another 1 week per, sorry, 1 day per each algorithm, right? So we won't go into those details, but just to have an idea of the idea that they are there, right? Yeah. So, and also some are open-ended questions. People don't have efficient algorithms to do those things, right? So we can go to the literature and find out. Right. So mining multi-level associations is one. We'll look at examples, right? And then the next one is mining. There's a typo there, mining. It's not mining, it's mining. Multi-dimensional associations, right? Right. And then mining quantitative associations and mining interesting correlation patterns, right? So let's take each one of them and try to see what we are trying to say here. Mining multiple level association rules. What do we mean that? Mean by that? Yeah, so we did not introduce this idea of what we call a concept hierarchy in data, there's always concept hierarchies, right? So for example, I can give you the example from this market basket or a supermarket example, right? So if you take the milk, right, so you can think about the milk as all types of milk, or you can separate the milk into 2% milk and skim milk. Skim milk is, let's consider skim milk as the normal milk. In Sri Lanka, the fresh milk and the low fat milk, right? So two categories of milk, right? So when we are mining or when we are looking for patterns, do we pattern mine at the higher level milk, or do we pattern mine at the lower level? Or we can even go lower, right? For the low fat milk, we can even think about the different brands. And yes, I don't know, these days we don't find any milk on the shelves in Sri Lanka, but right, we think about 2 years back, or maybe 2 years into the future, when we have multiple brands of milk available, do we do it at the overall milk level pattern mining, or do we do it at the anchor, Nespresso, Highland, Ratti, all those different brands that we have, right? So yeah, so there could be patterns that you get from who buys anchor milk and some other thing, right? So if you want, you can go to that level, or else you can do it at the higher level, right? So some of these algorithms have been extended to actually mine them at different levels, multiple level. That's what we mean by multiple level association mining. But we have to be very careful when we do it at the lower level. We can't expect the same support level, right? So at the milk level, if you expect a 10% support, we can't expect that to be there if you do low fat whatever Highland milk, right? So that would, however, right? So we need to adjust our thresholds when we are running the algorithms. I didn't mention that. I do have been so when you are running algorithms, the time that you would take to process the data set depends on the support that you put, right? So if you put a very low threshold, we saw in that graph, right? So you won't be able to finish that algorithm, right? If you put a 2 of a very high threshold, you might find very few rules, right? So we need to make sure that you balance it and come to a proper, right? And once again, when you talk about multi-level associations, also we need to make sure that you find appropriate level confidence, right? Appropriate level support levels to put there, right? Confidence doesn't make a difference, but support wise, we need to be conscious of what we put, right? Yeah, and also when we do these multi-level associations, there could be redundancies, right? So this example shows that, right? So if you have a rule saying milk implies wheat bread, right? So that means people who buy milk will buy wheat bread with a support of 8 and confidence of 70%. And we come up with a rule saying 2% milk, people also buy wheat bread with the support of 2% and confidence 72, right? So yeah, so we can say that the first rule is an ancestor of the second rule, right? So I mean, because milk implies wheat bread, that is because actually 2% milk also implies wheat bread, right? Yeah, so so there's no point in highlighting that, right? There's no unusual behavior in that, right? So that's why we say it's expected, right? When milk has 8% support for wheat bread and with a 70% confidence, 2% milk with wheat bread with smaller support with the same similar kind of confidence is already known, right? So that's something that we need to keep in our mind, right? Yeah, so so that's about multi-level association mining, right? The first topic, right? Mining multi-level association, right? So let's look at in the title slide, it said miming multidimensional associations, but it's mining multidimensional associations, right? So yeah, so single dimension association rules. I mean, dimension means the columns, right? Single dimension association rule means I mean, example is given: buying something would imply buying bread. Sorry, buying milk would imply buying bread, right? A multidimensional rule would be where you have more than one dimension, right? So age is something, occupation is something, and you would be buying a Coke, right? And also we can have what you call these hybrid dimension association, right? So what we mean by hybrid associations is that you have age and popcorn together on the left hand side and then Coke on the right hand side, right? So why we call it hybrid means, if you notice, it's earlier we put the age as one category of attributes, occupation as another category of attributes, and Coke as a product that you buy as another, right? So in a hybrid dimension association, we might have both Coke and popcorn together in the rule, right? So that's what we mean by hybrid association rules, right? Yeah, and categorical, we need for example, categorical attributes, and we need, I mean, there will be finite number of possible values, and there won't be any ordering among the values, right? And when it comes to quantitative attributes, there is some, some order, implicit ordering among the values, right? So, for example, if you take the age, there is some ordering, right? So, therefore, we need to consider that when we talk about mining associations, right? So, how do you take care of that, right? I mean, for an item, categorical item, there's no order. We can take it wherever we want. But when it comes to quantitative attributes and when we are doing association rule mining, like putting age into it or salary into it, then we need to consider those things, right? So those are things that we need to consider. Yeah, so once again, people have done research. I would leave this slide for you to have a look at it later, right? So we're running a bit out of time. I have 7 slides and 3 more minutes. I'll take maybe 5 minutes from you for this. Right, so let's look at one small example of quantitative association rules. Right, so where we have quantities, right? So in this case, the dimensions are the salaries and the age, right? Yeah, so yeah, so especially when it comes to quantitative associations, we need to have some kind of discretization. Right, so we need to discretize, otherwise we can't talk about items, right? So, right, so in the case of salary, what we have done is we have started from 10K, less than 10K, sorry, 20K, and then 10 steps we have put the data, and then for the age, we have put each age value into the different categories that we have, right? And when we are, yeah, right, and then we do the association mining, and we may find some rules like what is given here. Right, where I mean, high support rules to say that I really don't know what the left hand side is. Yeah, left hand, we actually both, only the left hand side is visualized here, right? Age is something, income is something, and they buy high resolution TVs, right? So what I want to show is it's a quantitative association rule, but on top of that, we can combine this. Now we have if you look at the graph, you see 4 crosses, right? That means we have found 4 rules, right? High support, high confidence rules. What we could do is we could combine them together to form one rule, because if you look at, it's because of our discretization that this has come like this. So what we could say is we can come up with one rule to say that age between 34 and 35 with an income level between 30 and 50K would buy a computer. Just one rule from 4, right? So that is something that we need to keep in mind when we do quantitative association rules, right? Yeah, that's what I want to highlight. And then there are other ways of looking at the interestingness of a rule, right? So we looked only at the confidence, right? Just to get the basic understanding, but lift is also another way of looking at the interestingness of a measure, right, or a correlation, right? Right. So yeah, so actually this example shows a case where confidence might fail, but lift might give you a better result, right? So play basketball and eat cereal. We have a support of 40% and 66.7 confidence. But overall percentage of students eating cereal, I mean, let's assume that we all know that overall percentage of students eating cereal is 75%. That means this 66%, 66.7 is not that significant, because anyway, a lot of people are eating cereal. So there's no significance in saying People who play basketball are eating. Anyway, people are eating cereal, right? But if you look at the play basketball board and people who do not eat cereal, 20% and 33, that's a kind of a more significant thing, right? Right. So by using lift, we can sometimes avoid this, right? But once again, there are limitations on lift also. We can't say that lift is the best, otherwise we could have used lift all the time, right? So it's good to maybe check both the confidence and the lift also, right? So how you calculate the lift is given on this slide. I don't want to go into detail. The example is also given, right, because of the time, right? Yeah. So, and this slide actually shows a few different interesting measurements. Once again, this is also a very open-ended scenario. These are most of the widely used interesting measurements. You can write papers on these interesting measurements. Right? If you can come up with an application where you got some good rules simply because you had a modified or you had your own novel way of measuring the interestingness, that would actually be publishable work, right? Yeah, so the last topic of the day, the topic for this session is constraint-based query mining, or I mean constraint-based association mining. What we mean by constraint-based association mining is that we love the standard algorithm to work, but on top of that standard algorithm, we put a constraint. In other words, we put a kind of a filter so that we only get the results that we want. We don't want all the results, right? So, I mean, anyway, we get to the high, I mean, on top of the frequency, we put another constraint, right? Frequency is anyway a constraint. Frequency is anyway a filter for us to get the results that are interesting. But on top of that, we put another constraint to filter out and get what we want, right? Let me show you an example. Yeah, there are lots of examples here, right? So, for example, when we are doing association mining, we may not be, I mean, if you're doing for house prices or something like that, or house sales or something like that, we may not be interested in very low valued sales, right? Maybe what we could do is we put a constraint and filter and say, okay, we are only interested in things that are higher than $200 or something like that. And so let me I mean, the thing is not putting the constraint. The thing is, how can we modify the given algorithm to put this constraint, right? So that's what we are looking at, and this slide shows how we can do that. I don't have animation here, but let me very briefly explain. Yeah, so my example scenario is that we have a collection of items in a supermarket, and then we are not worried about the small items like maybe safety pins and what do you call them? Satapahe items, right? Small items, right? Less than ₹1, right? So they are there because in the supermarket because people want to buy them, right? But from a business point of view, they are not making a big return for us, right? So therefore, we want to ignore them. But the data set contains everything, right? So we don't want, we can, if you want, we can filter that out and do the mining, right? But we want to keep that also in the database, but we want to modify the algorithm so that we can identify the rules that have a better, higher value, right? Higher valued items only, or maybe the collection of the pattern, collection of the item set should be above a certain value, right? So we can do that. And so that's what we are showing here in this example. I am repurposing this example to say that the item number indicates the value of that item, right? So yeah, so my constraint is to say that total price of a collection of items should be actually I'm taking the opposite of what I said earlier, less than 5, right? Right. So if ever the price is more than 5, we would not be taking it, right? So that's the constraint, right? So therefore we do the first scan to find the frequent patterns, and the next, when we are filtering, in addition to looking at the support, we will also look at the price, total price, right? So since 5 is greater than, is not less than 5, we drop that and we keep only 1, 2, 3, and then in the next step we once again do the scan, right? Item scan for the combinations, and then we find that we end up getting a set of frequent patterns, and we drop the ones that are low frequent. But then as we have a constraint for the total price to be less than 5, we drop 2 3 to 5 to 3 5, and we only keep 1 3, right? So, and that is the only item that is going to end up, right? Okay, so it's a very short crude example of that, right? So yeah, let me summarize. I've taken 6 minutes. Let me take 1 more minute to summarize. We talked about frequent pattern mining, which is a very important task in data mining. In scalable frequent pattern mining methods are there. We talked about a priori. We talked about FPgrowth. We very briefly talked about vertical formats, or one example of Viper, right? And then we talked about mining a variety of rules, a variety of interesting patterns, different, I mean, not the standard patterns, but extensions to the standard way of looking at associations. And then finally, we looked at constraint-based mining. We did not look at mining sequential pattern and structured patterns, but we can extend what we discussed to mining sequential patterns and structured patterns. And we can also think about how we can extend this to multiple applications, which we did not talk, but we can extend it. Right. Okay. So that would bring me to the end of the session. And once again, there's another small exercise that you can do as a practice exercise. I would strongly encourage you to do that. Any questions regarding this session or the project? I want all of you to get into groups and start on the project. And I think there are some deadlines for you to put a submission, right? So if you have any questions, please do ask now on the chat, or maybe you can unmute yourself and ask. Although the time has gone, I'll be here for 1 more minute. If you ask questions, I can be there for more than that. But if it is silent, completely silent, I will stay there for 1 more minute. Let me stop this recording.